Assalamualaikum and good evening. Today we like to present the title is Home Air Ventilator Fan. Let we introduce ourselves. My name is Safa Akila binti Siddiq. My metric number is Y97095.
My name is Shahrizal Mesidik. My metric number is 196879.
And my name is Muhammad Alif Aiman. My metric number is 197382.
Okay, first of all, I will go to the introduction part. Let me define the fan propeller. Fan propeller is an axial flow fan that controls no or less static pressure. It's called propeller fan with a sheet and aluminum metal. Motor mounted in the air stream driven through a six-bladed propeller fan. Physically, there is no difference between propeller and fan. Commonly, propeller fan is applied on objects whose primary purpose is moving. The fan has three main types that are used for moving, which is axial, centrifugal, and cross flow. While fan propeller categorized as axial flow blower, either with or without casing. Besides a set of features, the rotate hub and radiating plate can form a helical spiral. The performance applied in a fan propeller is similar to Archimedes screw. So I'll go to the basic theory for the fan propeller, which is several theory concerned propeller were proposed in the 19th century. The first describing a mathematical model of an ideal propeller that applied the momentum theory or disk accretion theory is developed by W.J.M. Rankine in 1965. The fan propeller is modeled with a thin disc generating a constant velocity along the axis of rotation and creating airflow along the propeller. Wall fans propeller axial flow fan type which is enclosed within a cylindrical houses or shroud. Wall fan propeller works by moving the blade in a forward direction, different in pressure between the front and back surface of its blade through it forces the blade to rotate in motion. So we'll look at figure 1.1 that shows the real propeller that we use the scale for our project. So this one is a real fan propeller, wall fan propeller. And figure 1.12 show that the fan propeller design that we're using a space claim to create this design. So I will pass to the Alif for the problem statement.
Okay, for the problem statement, we decided to analyze the characteristic of propeller to find the best properties that affect their performance, in which they can circulate the air ventilation the best. We decided to design three different propeller with three different pitch and angle of attack, which affects their effectiveness. In the designing part, each of three members will have their own modified with coupled specification with 300 millimeter pitch with angle of attack of 30 degree, 400 millimeter pitch with angle of attack of 20 degree, and the last one will have 500 millimeter pitch with angle of attack of 10 degree. Okay, from all these 3D designs, we are going to investigate the best design for the propeller fans to operate at maximum capacity. So we're going into the modeling stage.
So thank you, Alif. So it's my part. We move to the modeling stage, that is 3.0. So 3.1 is we do the 3D designing in SpaceClaim. First, the house air ventilator fan was designed beforehand in SpaceClaim software based on the actual dimension of the house air ventilator fan. This 3D design basically had the same dimension of fan blades, body, and number of blades. But the only major difference was in the pitch used, which can affect the angle of attack, that is 300, 400, and 500 mm. So up. up a little bit.
Sorry.
So we will move to the table 3.1.1. That is the characteristic of each design. So we have here design 1 with the overview you can see, and the specification, that is the pitch is 300 mm and the angle of attack is 30 degree. And for the design 2, you can see here the overview is almost the same, but the specification is different. That is, the pitch is 400 mm and the angle of attack is 20 degree. And for the design 3, the specification is the pitch is 500 mm and also the angle of attack is different. That is 10 degree. And then we move to the geometry modeling in ANSYS 90.2R. Down.
Going down.
More.
All right.
Okay, you can see the figure 3.2.1 that shows the fluent analysis system. So basically, first, the FFF was set up to insert and model geometry. After importing our design model in the geometry, we prepare our model in SpaceClaim first to detect and fit any errors that occur in the model. Under the repair toolbar, we will use tools like Speed Edge, Extra Edge, Duplicate, Small Faces, Simplify, and Inexact Edge to detect and fit error in the models. Scroll down.
Okay. All right.
And the figure 3.2.2 shows the SpaceClaim repair toolbar that we used before. And then next, we use the interference, sharp edge, and clearance tools under prepare toolbar to detect and fit small error that appear in the model even further. You can see the figure 3.2.3 shows the prepare toolbar. And then after the model has been fixed in SpaceClaim, up a little bit.
All right.
In the SpaceClaim, it was imported to Design Modeler. In Design Modeler, we create the enclosure using the enclosure tool, and then the Boolean tool to create the Boolean. And you can see the specification of the enclosure here in the box in the figure. Scroll down a little bit. Figure 3.2.4 show the details of the enclosure, and figure 3.2.5 show the detail of the Boolean. And finally, the name section feature will be used to distinguish the inlet, outlet, and the wall body of the enclosure. You can see figure 3.2.5, 0.6, and 0.7 show the inlet, outlet, and the body of the enclosure.
Okay.
And then the setup things were applied to all three designs. Each step was repeated exactly the same for design 2 and 3 also. Thank you.
Okay, for 0.0 is meshing. Meshing is a process after you done for design in a geometry in ANSYS. So meshing is a process of separating complex geometry into a simple element that can be used as discrete local approximation of the greater domain. The mesh has influence on the accuracy, convergence, and speed of simulation. So they had a few steps in meshing. So after the geometry has been modeled successfully, the machine setup was started by clicking the mesh category in a fluid flow model. So after after you click the mesh, and it will display the process of mesh. So first of all step, you must name the site. First, you must name the inlet, the outlet, and the body. So in a detail of mesh, the geometry setting was U in a display style. After that, fluency was chosen in the sovereign preference section. In the adaptive sizing section, yes was chosen. Generate mesh was clicked. The step was a repeat for design 2 and 3. So at the slide, you can see figure 4.1. This design will already generate, so it's already mesh. The color will be into a gray like this. Okay, so for the mesh information table, domain, the solid is 29319. So the number of element is 1,353. The mesh quality is a medium. So that's all for the meshing step.
Okay, as for the Fluent, once the mesh was successfully produced, the next part of the process was to set up the Fluent, which include all important parameters for this analysis that will then evaluate the action of our desired CFD. This section of the report will briefly address the steps taken to complete the measurement. So in the table 5.1, which we tabulate the parameters of simulation, which is the velocity with 70 meter per second, temperature at 1 atm, pressure will be at the standard room temperature. What? Oh, okay. It's upside down actually. The temperature is at the standard room temperature, and the pressure is at 1 atm. The density of air will is 1.225 kilogram per meter square cubic. Okay. So in NCs, there were a few components that were specified under the setup category, that is model, material, and boundary condition. For this analysis, the Fluent model that was used was the viscous model with K epsilon. The material used were air as the working fluid and aluminium for solid. Next, the boundary condition at inlet were defined based on the parameter velocity of our study in the figure 5.1 below. Okay, here is the figure. Okay, so after that, we undergo the solution category. Drag and lift coefficients were added in report definition. The force vector of drag coefficient was set to negative z, since drag force acted in the opposite direction of the air velocity vector. Lift coefficient's force vector was set to negative y, since the aim of this analysis was to investigate the down force. Okay, the figure 5.2 shows the report definition setting. So the next step was to do the initialization under the solution tab. This method was used for this analysis was hybrid initialization, since the analysis held in the general environment or at normal condition. Then after initialization, we run calculation tool. And we put the number of iterations, 200 iterations at maximum to ensure the computer's performance. Okay, next we calculate the button was clicked to complete and compute the CFD. So here's the parameters for the calculation. Okay, after the calculation was completed, the drag and lift coefficient were computed from the report definition. Finally, the CFD post was utilized and manipulated to obtain the velocity streamline, velocity vector, pressure contour, and velocity contour of the ceiling fan. The results from this analysis will be displayed in the appendix. So this is the results.
Okay, so for the result, we obtain for the from the solution step. So here is the table of the result. We have a design 1, design 2, and design 3. Angle altered 30 degrees is represent for 300 pinch. 20 degree is represent for 400 pinch. 10 degree is represent for 500 pinch. So for design one, lift force is 95.089061. Drag force is 0.1887. Lift coefficient is negative 3.4049. Drag coefficient CD is 0.0069. For design 2, lift force is 72.7948. Drag force is 0.3199. Lift coefficient is negative 2.6067. Drag coefficient is 0.0115. For design 3, 10 degree angle of attack. Lift force is 55.7503. Drag force is negative 0.5116. Lift coefficient is negative 2.1038. Drag coefficient is a negative 0.0183. So for all the results, we can take the design of the graph. So figure 6.11 show the graph the static pressure against position of a design one. So this one we can see the graph for a design one. Okay, so for the second, figure 6.12 is the airflow of the design one. So you can see the airflow, and then next figure 6.13 show the fan, show the wall fan ventilator velocity of the design. Next figure 6.14, it shows the wall fan ventilator pressure of design one. Okay, next. So you can see for the next 2 and 3 design, which is similar with the design one. Okay, that's all.
Okay, as for the discussion, from the 3 designs, we can see that design 1 has the highest lift force compared to other designs, which is 95.086 Newton. Okay, this proves that higher angle of attack results in higher lift force until it reaches the critical angle. Okay, as for the drag coefficient, design 2 has the highest value, which is 0.0115. Meanwhile, design 3 has a negative value of drag force, in which by definition means there is a reduction in drag force, since a positive drag force indicates a force that goes against the force of thrust. Okay, but from the results, there is an error in design 3 because by definition, drag coefficient can never be negative, since the drag force cannot be negative in steady flow. So the identified error that was done during the computational error was determined to be during the process, which is during the solution in the step of ANSYS program. Okay, when running the initialization process, the console box shows a warning message, which is as in the report. So probably this is the cause for the errors in the results obtained. Okay.
So as for the conclusion, so to conclude, from our study, we managed to observe the effect of the angle of the house air ventilator fan on its performance in bringing out the hot air to the outside. Based on the result obtained, the design 1 is chosen as the best design compared to design 2 and 3. Design 1 are said to have highest lift force, which means that it has highest efficiency to bring out the hot air from the inside of the house to the outside compared to design 2 and 3. Thus, the objective of this project, which is to investigate the problem of choosing the best design of the house air ventilator fan, is achieved. So for the reference, there are the list of the reference that we use for this report. And then for the group member contribution, you can see I, Sharizan, do the part of modeling stage, conclusion, and compiling and recheck. And Safa Akilah do the introduction, meshing, and the result part. And finally, Alif Aiman doing the problem statement part, fluent. So
Okay.
I think that is for our presentation
you
for
finish.
the
For
report
this
of
project,
the house fan ventilator. So that's it.
That's all
Thank
from us.
you for the.
Thank you. Thank you for
Thank you.
listening. Bye bye.